Captions in English, please. So this is the third video of chapter 8, and we will learn to convert between mass and number of atoms, or vice versa, between a number of atoms and mass. So let's use that first example, and the question is, how many aluminum atoms are in an aluminum can with a mass of 16.2 grams? So we are given a mass of 16.2 grams of aluminum. We want to find how many aluminum atoms that they are contained in that mass of aluminum. So we will need, so first, let's say that between grams and number of atoms, there is no direct relationship, right? We know that we will need to go through moles because we can relate grams to moles and then moles to number of atoms. So we will need the molar mass of aluminum. And so for this, you look at your periodic table, and aluminum has a molar mass of 26.98 grams per mole. So the molar mass is the number below the name or below the symbol, and it indicates the molar mass if you use the units of grams per mole, and that's the number with the decimal. So that's the molar mass of aluminum written in as an equality. So 1 mole of aluminum is 26.98 grams of aluminum. Once you have changed your grams into moles, you can change the moles into a number of atoms using the definition of the mole, which says that 1 mole is the Avogadro number of atoms. So 6.022 times 10 to the 23rd atoms. So the concept map here shows how we will go from grams of aluminum, that's the given amount, to moles of aluminum using the molar mass, and then from moles of aluminum to atoms of aluminum using the Avogadro number or the definition of the mole. So the first conversion factor will change the grams to moles, and we will use the molar mass such that 1 mole is on top and the grams are on the bottom because we have a given amount of grams, and so this way the units of grams will cancel. And then the second conversion factor needs to cancel the unit of moles. So there will be the need for moles to be on the bottom and then the Avogadro number of atoms on top. So if you write all of these together with starting with the given amount of 16.2 grams of aluminum, multiplied by 1 mole of aluminum over the mass of aluminum per mole. So we see that the grams cancel. Next, the second conversion factor has the moles on the bottom so that we can cancel the units of moles. And we have the Avogadro number of atoms on the numerator. This way, we're left with atoms of aluminum. And so in the calculator, you do 16.2 times 6.022 10 to the 23rd. Remember to use the scientific notation here with the EE key. And then divided by 26.98. The calculator answer is 3.615878, etc., 10 to the 23rd. Here we keep 3 sig figs because the limiting amount of sig figs comes from the given amount, which has 3 sig figs. The molar mass has 4 and the Avogadro number has 4. And the 1 moles are always exact here. So that's the final answer here. It's the number of atoms of aluminum in a can of 16.2 grams. So if you look at the number of atoms, you expect to have a number, with a scientific notation with an exponent to the 20s, like here 10 to the 23, because, number of atoms should be huge like the Avogadro number. And this 3.62 10 to the 23rd is about half of the Avogadro number. So let's verify that the given amount was about half of the molar mass, because if we have half of the Avogadro number, that means we have about half of a mole. And so half of a mole would mean half of the mass. And so yes, this 16 is grossly half of 26.98 grams of aluminum. So this answer makes sense. Let's go through another example, and this time we'll change number of atoms to mass. And the question is, what is the mass in grams of a bar of gold that contains 7.802 times 10 to the 27th atoms of gold? So we have this number of atoms of gold. We want to find the mass in grams of gold. So again, there is no direct relationship between atoms and grams, and we will have to go through moles. So from atoms, we can calculate the number of moles using the definition of the mole. And then from moles, we can get grams of gold if we look at the molar mass. And so if you look at your periodic table, you will find that 1 mole of gold has a mass of 196.97 grams. That's the molar mass for gold. So the concept map looks like this. We start with atoms of gold. Using the Avogadro number, we will calculate the number of moles of gold. And from the number of moles of gold, we can retrieve the mass in grams of gold. So the first conversion factor will use the definition of the mole. And because we start with number of atoms, the number of atoms, the Avogadro number, will be on the bottom of the conversion factor and 1 mole on top. Next, we will use the molar mass. And because we have 1 mole in the numerator of the previous conversion factor, we will need the mole on the bottom of the second conversion factor with the grams on top. So if we put all of this together, we start our calculation with the given amount of atoms of gold multiplied by the first conversion factor such that 1 mole is on top over the Avogadro number of atoms on the bottom. This way the atoms of gold cancel, the units cancel. Next, you want to cancel the moles of gold. So because it's on the numerator in the first conversion factor, the 1 mole of gold will have to be in the denominator of the second conversion factor. This way the units of moles of gold cancel. And you have the grams of gold in the numerator. So all units cancel except for grams of gold, and that's what we are looking for. In the calculator, you do 7.802 times 10 to the 27 multiplied by 196.97 and divided by 6.022 10 to the 23rd. And here it is important that you use the scientific notation, because if you don't, and if you don't use parentheses around the Avogadro number, the exponent, the 10 to the 23rd will move to the numerator and will change the exponent to your answer to 10 to the 50 maybe, or 49, and it will be wrong. So the calculator answer is 2.5519, etc., 10 to the 6 grams of gold. The limiting number of sig figs is 4. The given amount has 4, the Avogadro number has 4, and the molar mass has 5 sig figs. So we need to keep 4 sig figs. And so we keep the 2.551. What comes after the 1 is a 9, so you need to round up to a 2. So it's going to be 2.552 times 10 to the 6 grams of gold. And so that's the mass of gold in this number of atoms of gold. So now let's do some concept check for practicing that. Calculate the mass in micrograms of 6.80 10 to the 25th atoms of iron. So we'll go over this first concept check here. So what is given is the number of atoms of iron, 6.80 times 10 to the 25 atoms of iron. we want to find the mass in micrograms. We have no relationship between these two. So, from atoms, you need most likely to go to moles, and then from moles to grams using the molar mass, and then from grams to micrograms using the definition of the microgram. So we will need the fact that there is 6.022 times 10 to the 23rd atoms of iron in a mole of iron. So this will allow us to change atoms to moles. Once we have a number of moles, we can change that to grams of iron using the molar mass of iron. So for this, you need your periodic table, and you should find that the molar mass of iron is 55.85 grams of iron. Once you have grams, you need to change to micrograms using the definition of the microgram. And 1 microgram is 1 × 10⁻⁶ grams, because the value of the micro prefix is 1 × 10⁻⁶. And so you rewrite after that the grams, the base unit of grams. So the concept map looks like this. We start with atoms. We will change that first to moles using the definition of the mole. Then from the moles to grams using the molar mass of iron. And then from the grams to the micrograms. So the first conversion factor will change the atoms to moles. And so because we start with a number of atoms, we will use the definition of the mole with the 1 mole on top and the Avogadro number of atoms on the bottom. Next, to change moles to grams, you use the molar mass, and you will need the mole on the bottom and the grams on top because you want to cancel the intermediate units of moles. Next, you want to cancel grams and be left with micrograms. So you will place the 1 microgram on top and the 10⁻⁶ grams on the bottom. So when you write the full calculation, it looks like this. You start with the given amount of atoms of iron, multiply by the first conversion factor that has the Avogadro number of atoms on the bottom so that the number of atoms cancel. And we have 1 mole on the numerator. So the next conversion factor has to have the 1 mole of iron in the denominator and the molar mass in grams on top. This way we cancel moles of iron. And then we need to cancel grams of iron. And so we will have the 1 × 10⁻⁶ grams on the bottom and the micrograms on top. This way we can cancel the grams of iron. In the calculator, you do 6.80 times 10⁻⁵, multiply by 55.85, and then divided by 6.022 times 10⁻⁵, and divided again, because that's in the denominator, by 1 10⁻⁶. Be careful, it's 1 10⁻⁶. It's not 10 times 10⁻⁶. The calculator answer is 6.3065, etc., 10⁹ microgram of iron. We have 3 sig figs in the given amount, 4 sig figs in the Avogadro number, 4 in the molar mass. All the others are exact numbers. So we need to keep 3 sig figs, the least number of sig figs. So we keep the 6.30. What comes after the 0 is a 6, so we need to round up to a 1. So it's going to be 6.31 times 10⁹ micrograms of iron. And that's the mass for this number of atoms. It's a huge number of micrograms because really this should be milligrams, grams, it should be even kilograms to make more sense. So second problem, calculate the mass in grams of lithium that contains the same number of atoms as 1 kilogram of zirconium. So interesting. So you have a number of kilograms of zirconium, so exactly 1.00 kilograms of zirconium. So that's a mass. And you want to find the grams of lithium. So, you know, you have zirconium, but you want to end up with lithium. So here you have to first change the kilograms of zirconium to grams, because to be able to change, you know, zirconium to lithium, we will need to say that it's the same number of atoms. For the same number of atoms, that means you have the same number of moles, right? Because a given mole has always the same number of atoms in it. So by having the same number of moles of zirconium as you have lithium, then you will have the same number of atoms. So that means we need to go to moles. And so from kilograms, we need to go to grams, and then grams to moles of zirconium. And then that number of moles, we'll consider that now it's moles of lithium and change that to grams of lithium using the molar mass of lithium. So we will need the fact that 1 kilogram is 1,000 grams. That's the definition of the kilograms here. You change kilo by its prefix and that by its value, and it's 1,000. 1 mole of zirconium, if you look at your periodic table, it's equal to 91.22 grams of zirconium, and 1 mole of lithium is 6.94 grams of lithium. So the roadmap or concept map will look like this. Oh, it's missing a piece actually. So from kilograms of zirconium, we will change that to grams of zirconium. And from grams of zirconium to moles of zirconium. And then we'll have our moles of lithium. And then from there, we can have the grams of lithium. So it's missing another step here from moles of lithium to grams. So the first conversion factor here will be using the fact that 1 kilogram is equal to 1,000 grams, and we will have the 1 kilogram on the bottom of the conversion factor because we are given a mass in kilograms. So we want to cancel the units of kilograms. Next, you want to cancel units of grams with the molar mass of zirconium. And so the grams will be on the bottom, the 1 mole of zirconium on top. And then to go from moles of zirconium to, it's actually grams of lithium here, because at that point you will have a number of moles of zirconium. So using the molar mass of lithium, we can get grams of lithium. So, you know, the last box here should say grams of lithium. So the solution will look like this. We start with 1 kilogram of zirconium. You change that to grams by using the fact that 1 kilogram is equal to 1,000 grams. And we have 1 kilogram in the denominator so that we can cancel units of kilograms. So at that point, if you stop the calculation, you would have grams of zirconium. But we need to change that to moles. So you use the molar mass of zirconium and you want the grams on the bottom because they will cancel with the grams of zirconium in the previous conversion factor. So 1 mole of zirconium on top. If you were to stop the calculation at that point, you would get a number of moles of zirconium. And because we want the number of atoms to be the same, that's equivalent to say that we want the number of moles to be the same. So then at that point, because we have a number of moles of zirconium, now we can simply use that number of moles of zirconium and change it to, or moles of lithium, and change it to grams of lithium. So we will use the molar mass of lithium with the 6.94 grams of lithium on top and 1 mole of lithium on the bottom. And so when you calculate this, it's 1.00 kilograms of zirconium times 1,000, to change that to grams, divided by 91.22 to get the moles of zirconium, and multiplied by 6.94 to get the grams of lithium. And that's 76.0798, etc. grams of lithium. So we have 3 sig figs in the given amount. 1.00 has 3 sig figs. The 2 zeros are significant. The definition of the kilogram versus grams is exact. 1 moles of zirconium or lithium are exact, and the molar mass of lithium is only 3 sig figs as well. So, but the molar mass of zirconium has 4. So the limiting number of sig figs is 3. So we will keep the 7, 6.0. What comes after the 0 is a 7, so you need to run the 0 up to 1, and it's going to be 76.1 grams of lithium. So you see that 1 kilogram or 1,000 grams of zirconium would have the same number of atoms as 76 grams of lithium only. So it's a much smaller mass of lithium versus the mass of zirconium, because zirconium has much bigger and heavier atoms than lithium. So you need a much larger mass to get the same number of atoms. So that makes sense.